this lesson, we will explore how to graph functions by combining multiple transformations, and we will be analyzing the resulting graphs. In order to do that, we want to recall all the different transformations that we have already explored to date. We're going to be graphing functions of the form y is equal to a, f, k, x minus d plus c. A, K, D, and C all impact our parent functions in a specific way. Now let's go through them. So looking at the summary of transformations, we have y is equal to a times f at x. That a value represents a vertical stretch or compression. If the value of a is greater than 1, then we know the graph will be stretched vertically by a factor of a. If, however, that value of a is between a fraction between 0 and 1, we know the graph will be compressed vertically by a factor of a. Now, that a value directly impacts our y coordinate, and we're multiplying each of those y coordinates by a. If a is negative, we see a vertical reflection, and that means the graph is being reflected into the x-axis. That negative impacts our y values. So what was positive became negative. We also looked and explored, what does that k value do to our graph? So if we have something like y equals k at x, that k would represent either a horizontal stretch or a horizontal compression. If k is greater than 1, there will be a horizontal compression by a factor of 1 over k. So we talked about that scale factor. Scale factor is always that value, 1 over k, and it directly impacts our x coordinates. If, however, that value of k is between 0 and 1, the graph will be horizontally stretched by a factor of 1 over k. If that k value is negative, we observed a horizontal reflection. So we have a reflection into the y-axis. So the x values that were positive became negative, vice versa. If the x coordinate was negative, it became positive. The other transformations we looked at were the horizontal and vertical translations. If we're looking at something being added or subtracted directly to x, if d, that value of d is greater than 0, we have a horizontal translation, right d units. If, however, d is less than 0, we have a horizontal translation, left d units. C value represents our vertical translation. If, however, C is greater than 0, then we have a vertical translation up C units. If C is less than 0, then it's a vertical translation or a shift down C units, and that directly impacts our Y values. So in general, if we brought this all together, we're going to say A represents, depending if it's positive or negative, we can say A represents a reflection into the x-axis. So reflection into the x-axis, or a vertical stretch / compression. The k value tells us we may have a reflection into the y-axis. Okay, if it is negative, or depending on the value of k, we can have a horizontal stretch or compression. The d value tells us whether we have a horizontal translation, left or right. And our C value tells us whether we have a vertical translation, up or down, depending on the value. Now, when we're doing these transformations, we want to perform all the stretches and compressions and reflections first before translations. And that means that A value and K value, because we have to do the multiplication, just like BEDMAS, before adding or subtracting. Okay, looking at example 1, we're going to say for each function, determine the parent function first, then state the A, K, D, and C value to list the transformations. Okay, so looking at A, we have m at x is equal to -3, 2 times x plus 4r squared minus 1. So we always want to first identify the parent function. In this case, our parent function is the quadratic function f at x is equal to x squared. Okay? And then we read from left to right. Outside of the function, I always say, is your a value. So if you notice, -3 is outside the bracket. That is our a value. We always want to make sure that our function is factored. That k value always has to be factored out. In our case, it is. So we're going to say k is equal to 2. Keeping in mind that d value is kind of opposite what you see in the brackets, because standard is x minus d. In order for that to become x plus d, in this case plus 4, that value of d had to have been negative. So d is actually -4, and c is, as you see it, -1. Right? We're just practicing identifying the A, K, D, and C because that is very important when we do the transformations. So looking at B, the first thing we want to identify, what is our parent function? In this case, it is the square root function. So let's identify that first. And the reason why we have to identify it first, because we're going to need those key points from our parent function in order to apply these transformations. So we're just getting into the groove of identifying first the parent function and all the different transformations before we actually apply it to our graph. Now, A in this case, what is outside of our function, which is that 2 value. Within our function, notice -1/3 x minus 1. That is our k value, -1/3. Our d value is +1, and our c value is 5. Looking at the example C, we always want to make sure that k is factored out first. So if you notice, k is not factored out. So I'm going to just make a little note always, and this is very critical, before you decide on your values for A, K, D, and C, always factor out the k value. Okay, so before we even decide what A, K, D, and C are, we're going to factor that out. So h at x is equal to -1/3 out front. 2 is factored out of 2x minus 4. So we know 2x divided by 2 is x. -4 divided by 2 is -2. So keep in mind, we always have to factor out the k value. The parent function in this case is the absolute value function. A value, again, it's outside in front of our function, which is -1/3. The k value is being multiplied directly to the x, which is 2. My d value is 2, and c is 0. There is nothing being added or subtracted to the function in the end. Okay? Moving on to d. Again, critical, critical, critical. We always have to factor out the k value first. So d, in example D, we're going to say k at x is equal to 3 over. We factor out that number attached to my x, which is -2, and this becomes x minus 5 over 2. And then we can list and identify what A, K, D, and C. But before that, looking at our transform function there, our parent function would be the reciprocal. So we're going to say f at x is equal to 1 over x. My a value is that 3. My k value is -2. My d value is 5 over 2. And of course, c, we don't have anything added or subtracted there, so that would be 0. Okay, now that we've identified and practiced that, we're going to describe how to graph each of the following given functions Describe how the graph of each of the given functions can be obtained from the graph of y equals f at x. So we have a whole bunch of transformations happening. First, at first, we always want to make sure the k-value is factored out. In our example A, it is not. So we're going to do that first. There is a -1 attached to the x, so that must be factored out. So when we factored out that -1, we're left with x plus 3 plus 4. Now we can go from left to right, identify the A, K, D, and C, and then describe the transformations. So starting with the far left, we have A is equal to -3. Well, if A is negative, we know we have a reflection into the x-axis. Since A value is greater than 1, that would be a vertical stretch. Vertical stretch by a factor of 3. Okay, so that describes A value. My K value is -1. As K value of -1 is telling me that there is a reflection into the y-axis. Okay, x plus 3. Remember, standard is x minus d. That means that in order for that to become x plus 3, d had to be negative. So d is actually equal to -3. So the reality is it's always opposite what you see. Whatever is being added to the x value, that means that it had to have been x minus -3 for that to become plus 3. So that means we have a horizontal translation and it is left 3 units. And C is as you see it. C is equal to +4. That would be a vertical translation up 4 units. Moving on to B. Again, I can't stress enough, you must always factor out the K value. Now, B is a little bit trickier because it's not shown the way we typically see it. So you want to rearrange the transformations. This case, X should always come first. Okay, so with that in mind, we're going to factor out that -3 because that's what we must do before we decide on our A, K, D, and C. So we do that first. So I haven't even tried to identify those different transformations. I need to make sure that K value is always factored out first. And then we go from left to right. A is equal to 1/2. So that would be a vertical, because it's a number between 0 and 1, that's going to be a vertical compression by a factor of 1/2. Okay. Our K value, K is equal to -3. Okay, the negative tells me that it's going to be a reflection into the y-axis. Okay, so before we decide whether this is going to be a horizontal stretch or compression, we have to decide first what the scale factor is. The scale factor, just easier to see, a scale factor is always 1/k, which is 1/3. And I stress that it's the absolute value because the scale factor is always a positive value. The negative describes the reflection. So because the scale factor is 1/3, therefore we can say it is a horizontal compression by a factor of 1/3. The D value, again, opposite what we see, which is a +4. That means it's a horizontal translation right 4 units. C is equal to 2. So that is a vertical translation up 2 units. Okay, so now let's take this all and summarize it. Identifying A, K, D, and C leads us to mapping notation. Each step of the transformation could be shown and a specific point of f at x could be moved using mapping notation. As I stressed earlier, we needed to know our key points from a parent function. Each of those key points are going to be transformed based on what transformations are occurring. So I'm going to highlight this because this is like so critical and this will stay with you for a while. But each point on the parent function xy is being transformed accordingly. X over k plus d, those are the two that impact the x coordinate, ay plus c. Okay, so the factors a and k are being multiplied by those coordinates, d and c are being added or subtracted. So this describes exactly what will happen to each point of f at x and allows us to create a table of values to be graphed using the key points from the parent function. So example 3, given the graph of the parent function, sketch the transform function, state the domain and range of the transform function. So with anything we do in graphing, again, we have to make sure that k value is always factored first. And then we have to identify what the parent function is in order to apply the different transformations. So as you can tell here, x is not by itself, you can say. There is a negative out front, so we have to factor that out from both of those terms underneath their function. So negative 1 divided by negative 1 is positive 1 plus 2. Now looking at this function, this parent function is the square root function. So we're going to say f at x is equal to the square root of x. Okay, we factored out the k value, so now we want to identify a is equal to 2, k is equal to negative 1, d is equal to negative 1, and c is equal to positive 2. The parent function key points, which are already listed for us, are x is 0, y is 0, x and 1, y is 1, because the square root of 1 is 1. When x is 4, square root of 4 is 2. When x is 9, the square root of 9 is 3. We are going to use mapping notation in order to determine what are my points for my transform function. Now I'm going to remind you, x, y, each point in our parent function, it would be x over k plus d, a, y plus c. Okay, so we've already identified what a, k, d, and c are. So for our transform function, we're going to say x divided by negative 1 plus my d, which is minus 1. My a value is 2, so we're going to take a times y plus c. So 2y, because a is 2, and we plus c, which is plus 2. That means each point in my parent function, so all the x coordinates are going to be divided by negative 1 and then subtract 1. All my y coordinates are going to be multiplied by 2 and then add 2. Okay, so let's do that. So 0 divided by negative 1 is 0, minus 1 would be negative 1. Taking y equals 0, 2 times 0 is 0, plus 2 is 2. So that first point will be transformed based on all those transformations to negative 1 for x and 2 for y. We're going to follow with all the other points as well. When x is 1, 1 divided by negative 1 is negative 1, minus 1 would be negative 2. When y is 1, 2 times 1 is 2, 2 plus 2 is 4. Okay. When x is 4, 4 divided by negative 1 is negative 4, minus 1 would be negative 5. When y is 2, 2 times 2 is 4, 4 plus 2 is 6. Okay. When x is 9, 9 divided by negative 1 is negative 9, minus 1 would be negative 10. When y is 3, 2 times 3 is 6, 6 plus 2 is 8. Okay, so to graph that, when x is -1, y is 2. When x is -2, y is 4. When x is -5, y is, mm, oh, sorry, when x is -5, y is 6. And when x is -10, y is 8. So then, of course, we would have nice smooth curve. And then, of course, don't forget to identify and label the graph properly. So we can say y is equal to 2 -x minus 1 plus 2. Or we can use the factor form as well. Okay, so let's see. Have all these transformations happen? Did we have a vertical stretch by a factor of 2? It sure does look like it. Did we reflect our original graph into the y-axis? Absolutely. Have we undergone a vertical translation up and a horizontal translation to the left? Absolutely. Okay, so all those transformations are reflected on our graph. Okay, moving on. Oh, we forgot to state the domain and range. Now that we have the final transform function, looking at our domain, and remember domain are all the possible values for x. So in our case, x X is an element of real. However, X has to be less than or equal to -1. When we're looking at the range, Y is an element of real, or if it X is an element of real, either or. Y has to be greater than or equal to +2. Okay, let's try another one. We have y is equal to -3, the absolute value of 1/2 x plus 1, and that should show -1. Mhm. Before we start anything, we always want to factor out the k value. So y is going to equal to -3. I'm going to factor out the 1/2 from both. Keep in mind, if you take 1 divided by 1/2, right, that's the same thing as plus 2. And then don't forget, subtract 1 as my C value. So before we decide on A, K, D, and C, and K is the most critical, you must always factor out the K value. The parent function in this case is the absolute value function. So we're going to say f at x is equal to the absolute value of x. Okay, so the reason why we identify the parent function is that we have to take and can remember all the key points for our parent function. The absolute value function, if you remember, is our distance of x values of x's towards 0. So it's always positive. So if x is -2, the absolute value of -2 is +2. If x is -1, y is 1. Absolute value of 0 is 0, 1, 1, 2, 2. So that's our parent function. F at x is equal to the absolute value of x. We're going to take those key points from our parent function. We're going to transform them according to the transformations. A value is that number outside of our function, which is -3. Our k value is 1/2. Our d value, which is -2. And our c value, which is -1. X divided by k. So I'm just going to do this to the side. If we took x divided by 1/2, okay, we want to try to simplify this because that's what we're doing. If you look at the mapping notation, x divided by 1/2. Now, a fraction and fractional is kind of strange, so we're going to use our rules for dividing fractions. We keep the first, we take the reciprocal of the second, and then we multiply. So that actually will become 2x. So this would be 2x plus my d, which is -2, and then a, which is -3y plus c, which is -1. That means each values, okay, the coordinates in our parent function, those key points, they're going to be transformed accordingly. So we're going to take the x being negative 2, 2 times negative 2, which is negative 4, minus 2, which is negative 6. We're going to substitute y being 2. So negative 3 times 2, which is negative 6, minus 1, which is negative 7. Taking x is equal to negative 1, 2 times negative 1, which is negative 2, minus 2, which is negative 4. Negative 3 times 1 is negative 3 minus 1, which is also negative 4. Substituting 0, which is the easiest one, 2 times 0 is 0, 0 minus 2 is negative 2. Negative 3 times 0 is 0, minus 1 is negative 1. 2 times 1 is 2, minus 2, which is 0. 3 times negative 1 was negative 3, minus 1, which is negative 4. Substituting x is 2. 2 times 2 is 4. 4 minus 2 is 2. Negative 3 times 2, which is negative 6, minus 1, which is negative 7. So let's plot these points on our graph. At negative 6, we're at negative 7. At negative 4, we're at negative 4. At negative 2, we're at negative 1. At 0, we're at negative 4. And then, of course, at 2, we're at negative 7. Okay, so we're going to connect those. We should be using a ruler. And again, we just use these points, but these graphs we know do keep going. And then we can say our transformed graph is y. Oops. Okay. Y is equal to negative 3, 1 half x. Oops. 1 half x. One half x plus 1 minus 1. Okay, what would be our domain? What would be our range? So in this case, x is an element of real. There are no restrictions on x. X can be any possible value. Y, on the other hand, does have a restriction. So y is an element of real such that y has to be greater than or equal to negative 1. Okay, and that's our only restriction. Now, let's just reflect and see, did all these transformations happen? Well, a is negative 3. So negative tells me it's reflected into the x-axis. Well, the original parent function was definitely. Then there was a vertical stretch by a factor of 3. So it's been stretched. So it definitely looks narrower. Then we had the k value, which we have that would be a horizontal stretch by a factor of 2, because the scale factor was 1 over 1 half, which happened to be 2. Then we had the whole graph move over to the left 2 and down 1. All those transformations are reflected on our final transformed graph.